Hello, my name is Robert Siofe. I'm going to show you how to process data which you have received from the test on Instron machine. In this case it's going to be a tensile test where you have loaded sample to very low strain and then unloaded it. This test is usually done to measure initial stiffness of the material, as well as you can measure also initial Poisson's ratio. Typically from the machine you would get these type of files. You can see in this case it's 2 files, but if you have tested maybe 5 specimens you would have 5 files like these. These are, you can see, comma separated values, and let's open one of those. So this is the number 1, and you can see what you get in this file are text values, and you get header of the file which contains information about the specimen and conditions in the lab, date and stuff like that. For instance, this is a date, this is a specimen label, and of course label will be dependent on what you have entered during the test, temperature in the lab and humidity, which are quite important, but one of the most important is here is a cross-sectional area, and you should decide how you do it, if you enter correct value already during the test, or you calculate it here after the test with the actual dimensions of the specimen. I will a little bit rearrange these columns and this header in order to look at better, but before I do that I just again will explain what you have here. Like I said, header of the file containing general information, but then these are actually the results which have been recorded during the test. So you have time, and if you look to the end of the file, it was rather short test, under 10 seconds. You have extension in millimeters. This is a crosshead movement, how much the crosshead of the machine have moved during the test, and you can see it doesn't start from 0. And I will discuss this a little bit later on. This is a load. You can see again it starts with some strange value here, but we will take care of that later. And the load you can see increasing to positive values because it was a tensile test. This is strain, and this is strain given at this point. You can see it's with no units, it's millimeter per millimeter, not in percents as I would like to see it, but this is a strain from the extensometer, which is attached to measure axial strain or longitudinal strain, basically strain in the loading direction. And here we have strain gauge. This is a strain already in percent, and this is strain which is measured transversely to the specimen, transversely to the load direction, and measures transverse strain of the which is induced on the specimen. And you can see, of course, because it's a tensile test, we have axial strain which is positive, but because of a Poisson's effect, the sample is contracting in the transverse direction, so we have a negative values. So that makes sense. Okay, like I said, I'm going to rearrange a little bit the columns so they look better. So here how it looks when I rearrange them, and in my opinion it does look better, but of course it's up to you if you want to do that or you go directly to the data processing. But now you can see again the same columns: time, extension, load, strain 1 and strain gauge. Nothing has changed except the position of these columns and a little bit of the formatting of the values, so they look a little bit more clear when you look at them. So what do we do actually? What we are going to use in data processing? The aim here is to actually obtain stiffness and Poisson's ratio. So if I would plot, for instance, load as a function of time, I could see what the loading will look like. I'm not going to use actually time, and I'm not going to use extension. I am only going to use these 3 columns: load, strain and strain gauge. But we still can see how the test was done, because if I mark this column, I can actually plot not versus time but versus number of rows, but it's pretty much the same thing. And you can see, as I told you, you load it up and you unload it, and you do it for fairly low values in order to not to induce any damage, and then you process it to find Poisson's ratio and stiffness. There is one thing though, you see we have some kind of values at the beginning which are not really 0. So what to do with those? It's actually, you have to remove those values, because this is artifact and you don't really want them. Let's look at the values slightly a little bit closer. Let's say, let's look at the first 20 points only, and you will see what I mean. See here, nothing happens. This is actually when machine is not really loading specimen yet, but you already have recorded some data points. We don't need these because this is really artifact. There's nothing in these values. We could just simply delete them, if I could just do like this. But then you see we are missing data and it doesn't start from 0, so we can't just delete them. We will do something else. What we do, we actually take this point. You can see here it's number 5 in this case. Well, actually it's this point here, 7.1. This is the first value which has, or first point which has some meaning. So in that case we would call this one as a 0 value. Okay. So basically I will take now the curve and shift it from this position to here and assign this to 0. But how to do it in the right way? Well, this is what I'm going to show you right now. So I have created now 3 new columns because what I want actually do data processing in such a way that I have not a load as you get here, but I would like to have a stress in megapascals. I would like to have longitudinal axial strain in percents, and transverse strain, it's already in percent, so it goes here without changing in units. So how do you get stress in megapascal? And that's of course obvious. You divide load by cross-sectional area. And you can see in order to get megapascals, it's actually you don't need to do any changes of unit. If you just divide the load in newtons by cross-section area in square millimeters, you actually get megapascals. But what about that shift I was talking about? Okay, let's do it with a shift right away. If I wouldn't have to shift values, I would just divide this by cross-section area and I am done. But I have to shift it. So first of all, the shift will look like this. So remember I said that this point now is a new 0 value. I take this is C6 value, and I have to subtract the same value from all values in this column. So because it's the same value, I have to actually mark that it doesn't change number when I copy it to other rows. And now I divide by the cross-section area, and I have to also mark this, that Excel uses exactly the same value for every row. See, we have 0. Now I will copy this to all columns, to all rows, and I will get load in megapascals. I will do that in a moment. The same I do for strain, but you know, in order to get percents, I have to multiply this strain by 100. Because it's unitless here, millimeter by millimeter. And you could say, why would you want to shift this? It's already zeros. Yes, that's true. But I already moved this. I shifted load. I also have to shift all of the columns in the same way. So now already I decided that I'm gonna do this as a new 0. I will do exactly the same for the strain, even though the zeros are already there. But I will start with 100. Remember, I want percents times, and now I'm shifting exactly the same way as I would do for all columns. Of course, it doesn't change anything because the values are 0. But to be consistent and to use it for the next specimen, you will see that it's good to have exactly the same way. Okay, see, this is an error because actually I needed to shift it from this row here. So actually the row number has to be 6, not 3. So, see, now it's a correct shift, see? C6, C6, D6, D6, and times 100. And if I now copy it in the whole column, I'm getting strain in percents. Now strain transfers, it's already in percent, so only shift is needed, and I am going to do exactly as I did before. E6, 6 row here, minus E6, but the same value for the whole columns. Here we have it. You see now it's very nice. We start from 0, and I just remember to copy everything into until the end of the file. Now I have copied this to the end of the file. You can see very nicely goes to 0. Okay, because it shifted, you see these last values actually don't have any meaning because I shifted the whole thing upwards. But we will not use these values anyway, so for now I'm not talking about it. But if you would have sample going into failure, then you would need to remove that tail of this data. Now what I will do, now you have all the data, so what you have to be done, you have to plot stress strain curve, so stress as a function of strain, and also transfer strain as a function of longitudinal strain. Let's just do that. So I have created this plot, stress strain. You can see very nice straight line. And remember when I showed you first load, well, I was plotting load as a function of time, it was up and down. And we don't really see it here because now it's stress strain, and we don't see it because loading and unloading curves are coinciding, because this is very nice linear elastic material. There's no deviation, no damage. It's very linear, goes up, and it returns in exactly the same on exactly the same line. Well, maybe there's some scatter, but very, very little. So it's really nice material in the sense of there's no non-linearity and there's no damage. And there's no damage because we actually only loaded it up to 0.3 strain, which is very good. It's very low for composite. There's no damage, so we can actually obtain stiffness, initial stiffness of material with no damage. Just remember that stiffness can be obtained from the whole curve or from the part of the curve. We usually do it from the part of the curve, just to remove some strange things that may happen at the very beginning and at the very end when you start unloading a sample. And usually you would do that from unloading curves rather than from loading and unloading together. But in this case, of course, because the lines are coinciding, it's pretty much the same thing. I also have made a plot for Poisson's ratio, and this is how the plot looks like. You see the difference, very nice straight line with no scatter and a lot of scatter. And that's because this is actually, I can tell you, even though it doesn't say anywhere, this is a cross-ply laminate carbon fiber, and Poisson's ratio is actually very, very small. So you can see you load up to 0.3%, but response from strain gauge is really very small. It's very small strains we are measuring, and that's why there is a scatter. It's of course related to the accuracy of the equipment and stability of the temperature in the lab and stuff like that. So nevertheless, there is definitely a trend, so we are able to obtain Poisson's ratio. But also in this case, we are not going to use the whole curve. We are going to use it only from 0.05 up to 0.25%. This is usually what we use. How to do this? Of course, you could just delete all the results from here, but I prefer always to have complete curves and then curves specially made for calculation of stiffness and Poisson's ratio. How do I do that? Well, it's actually quite simple. Let me show you. Let's move this aside for now. And what I will do, I will actually duplicate this set of data, and I will do it in such a way that I will really just say, okay, this value is equal to this one. Okay, exactly the same result. There's no difference. See? And then I will copy all of this into the columns, and I will be cutting out everything that is smaller than 0.05 and everything that is larger than 0.025% strain. Okay, you see, for instance, here we haven't even reached 0.05, but if I just extend it a little bit, you can see that's below 0.05. That will go away. Okay, so I will do that, and then I can plot again these results and use them to process data to obtain stiffness and Poisson's ratio. So I made the columns, I cut data which are not needed. You can see now that it starts 0.05, go up to 0.25, not more than that. Again, go from 0.25 to 0.05. This is unloading part here, and this is loading part here. So what I do now, I still can plot loading and unloading together, and this is what I have done here. See, now it goes from 0.05 to 0.25%, and this is this new data set. But it's still going unloading and loading together, just for now to show you what is the difference if you use all of them. What I'm now gonna do, I have this line, and I will use trend line to obtain stiffness. Not only 2 points of the curves, otherwise I wouldn't do all this procedure here. So what I am adding, I'm adding trend line. I would like to see equations of that trend line, and I would like to extend it a little bit so I can see that it's actually going through. And I can change color just, you know, to make it nicer. Okay, so here you can see it. This is a trend line, and it goes through experimental results we have here. And it's perfectly linear because that's what I have chosen, a line. It doesn't go exactly through 0, but that's okay because we have some scatter anyways. But it's almost perfect line. Look here, see? If this R-square coefficient is 1, it means it's perfect line, but it's very close to the unity. Now, what do I get actually? So see this equation here? This coefficient here means actually coefficient between stress and strain, and that's nothing else as stiffness. However, what units is it in? Because we have percents here and because we have megapascal here, the units are a bit strange. You have to divide this value by 10, then you get gigapascals, okay? Dividing this by 10 gives you gigapascals. So in this case, the stiffness of the specimen is 57.9 GPa. But remember, I told you that these are results still from a stiffness of all data, meaning it contains loading and unloading. And I told you that it's better to actually measure stiffness from unloading because we know for sure then that it's not going to fail, or sorry, not going to fail, but it's not going to have any damage in the sample when we do that. So what I did, I actually plotted separately just to show you how it works. I plotted separately loading results and unloading, and here you have the graphs. I moved them a little bit down. Now we can move them back up here so you can see them better here. I already did even a trend line. I just want to show you, see this? Here we have data from loading. You see it starts from the low value and goes upwards, and that's what we plot here. And this graph here is actually from unloading. See, it goes from the highest value down to the lowest. What about the results? Well, you can see here where we had all data, it was 57.9. And if you look at the loading, it's 57.8, almost straight line as well. And from a case of unloading, it's 58. So it's not really big difference, and that's understandable because we have such a nice linear material. What I did also, I wrote these values down here. You can see loading 57.8, unloading 58, and of course this one is in between these two values because it goes, of course, loading, unloading. So that makes all sense. And we have calculated the stiffness. When you will do it, you don't need to plot all of these graphs. I suggest that you plot the whole curve just to see how it looks like, and then that you plot one which is unloading, where you actually do your calculations. So you may have a little bit different approach how you do this. You don't probably need to have Excel sheet which looks exactly like mine. You can have a different layout if you want to, but the important part is that when you do the stiffness calculation, you need to use it in a certain interval from unloading curve. What about the Poisson's ratio? Well, let me show you how that's done. So, in order to obtain Poisson's ratio, I have to plot transverse strain as a function of longitudinal or axial strain. And here is all data, loading, unloading. You can see, as I showed you before, quite a bit of a scatter, but still we have very good trend. It's definitely linear. Works well. Of course, it's far from being 1. You see here, it's not as good as it was in case of stiffness, but fairly good. So now what we need, again, we need a coefficient between this strain and this strain, and you can see, because if you remember definition of Poisson's ratio, it would be, we need Poisson ratio LT. So that would be this strain divided by this strain with a minus sign in front. And here we have our coefficient. Of course, now we are not using minus sign because minus sign is in equation. So Poisson's ratio in this case is very small. It's 0.0479. And I mentioned before, this is a cross-ply laminate carbon fiber. Actually, this value is quite decent for this material. It is small, and it's in that order of magnitude you could expect for this material. I did the same for the Poisson's ratio in loading and unloading. You can see we have fewer points now because it's divided in two parts now. And we have Poisson's ratio here, 0.456 for loading and 0.0502 for unloading. I summarize these results so we can have a look for a better overview. You can see Poisson's ratio loading, unloading, Poisson's ratio loading and unloading. You see 0.0502, 0.05456. So the difference is a bit higher than here. That's because of a scatter, of course. And this value, where we use all data sets, is between these two, which again makes sense. Now you have processed your results. You got stiffness and you got Poisson's ratio. And you can have these nice graphs pasted into the report. Again, you don't have to use all of them, but just to show how it's done. Remember, please, to save your file in an appropriate format. You can see here it's now saved as a data sheet of Excel. Otherwise, if you don't save it, your changes will disappear if you save it back again in this comma separated value file. But now the question is, okay, I did it for one specimen. Do I have to do all this work for each sample? Well, yes and no. Yes, because you do need to process exactly in the same way all of the specimens, but you don't need to do it from scratch, and I will show you how to do this. So now, like I said, you have done it for one specimen, and let me show now. If you open specimen number 2, you can see you have exactly the same set of data. Okay, these two actually are, it's a little bit different because you have strain gauge 2 and strain gauge 3 here, which actually we haven't used, so I just will remove it so it doesn't confuse you. Otherwise, you see, this is a typical data set. It's exactly the same as it was before. You have time, extension, load, strain, and strain from strain gauge. So what we're gonna do, we are going to take these results and copy into the data sheet which we have processed here. First I copy a header. See, I copy only values. Now these are different values. And I will copy all values from columns in the same way. I go back to the data sheet here. And I select all the data. And I paste them. Because we have exactly the same columns, I can just go to the first one, and you see I paste only values. However, please be very careful. Now check that you don't have residues from the old file. And you see, in this case we do. That's because old file was slightly longer, and these are data points from the previous file, which you don't need. So what you have to do, you have to just simply remove these, because these do not belong to the same data set. So just say delete, and you get rid of that. Okay, you see we have some problems here because we deleted some of the values. That's okay, it will be fixed, but you can also remove these because this is just artificial. Remember, data sets were shifted. But that's not all. Now you have to check the shift. Remember, the previous data we were shifting by 6 points, so this was our old 0. But now it's a different value, and we have to adjust our results. And it's very simple because we actually only have to adjust these 3. You see, instead of 6, we have to put 8. But we have to do it for all of them. And we have to paste into the columns, you see. Now it's all fixed, because these columns here are just a copies of this. And now, of course, this is not anymore specimen 1. You see it says specimen 2, so you can rename it. Or actually what you could do, and that would be a better choice, you just make a copy from the first sheet and then you edit the second one. But it's up to you. You can have a separate file for each of the samples. It's how you want to arrange it. The good news, we don't have to plot anything anymore because everything is done automatically since we adjusted the data. One thing you should check though. You can see here, remember, we need interval from 0.05 to 0.25. Okay, let's see if that interval actually is still maintained here. Well, this is good, starts from 0.05, goes up to 0.25, good, and goes down from 0.25. But you see here, this point actually still could be included. Not a problem. Just copy this in and you have this included. Very good. And this one should be excluded because it's outside the region we're interested in. So we delete it. And now we can go back to the graphs and you can see actually that it's automatically recalculates. In this case you see stiffness is 56.6 and we can actually put the new values here. And so on, you should put it for all of them. This is the only thing you actually have to do because otherwise you will have wrong data. So, like I said, just look at the data and copy them into the appropriate rows there where you make an overview. Similarly, these are recalculated automatically as well because we just pasted the new results in. And I already have summarized it here. You can see actually stiffness is very little change. It's actually pretty much the same from loading, unloading, and from the all data together. And this is a Poisson's ratio, which is a bit higher than for the previous sample, but pretty much in the same range. Well, that's pretty much it. Like I said, it's up to you what is the layout of your sheet, but this is how I usually do it. It works fine, and I mean, I like the graphs, to have graphs like this. If something is suspicious, I always can go back and look at it and decide what was wrong. Just really remember, when you copy sheets to process different samples, use one sheet as a template. You copy new data and you update your results. That's very important. Well, good luck, and that's all for now.